what we're going to do now is we're going to formulate our conservation of mass equation on the back of the solid skeleton. So before we had separate trajectories, we were driving conservation of momentum equation, we had separate trajectories from the reference configuration to the current configuration for the fluid and the solid, okay? Now we're going to say both the fluid and the solid, or the fluid and the solid that are, the solid and the fluid that are in the pores currently are going to move with the same trajectory. That is the trajectory of the solid. So but we're going to also allow for other fluid to move in and or out of the solid. Okay, well, that's just a cartoon, but we'll see what that looks like when we start, right? So we're going to start with our conservation of mass equation we derived before. Right, that's conservation of mass. Remember what I said? All of engineering is just 4 equations. If you just start with those and you just start working through things, you'll get somewhere. Right? Conservation of mass, momentum, energy, second law. If you're an electrical engineer, Maxwell's equations. All right, so now what we're going to do is we're going to go ahead and just write this for the fluid. So we'll put the fluid subscript there, and then we're going to use our previous definition that the density of the fluid is equal to the volume fraction of the fluid divided by, or times the local density of the fluid, right? So the first row F without the bar over the top, remember, is the density of the fluid, or the mass of the fluid divided by the total mass of the mixture, right? The second one is what we typically think of as the fluid density, right? So it's the mass of the fluid divided by the volume of the fluid, right? And phi is the volume fraction in the current configuration. All right, we're also going to define a relative velocity vector, that is the amount of fluid that moves relative to the solid. So we'll have a term like that. So velocity of the fluid minus the velocity of the solid. And so, from that, then we could, this is the velocity of the fluid also in the conservation of mass equation. So if we solve for the velocity of the fluid, then we get that, and we can plug that back into the equation, okay? So I'm going to go ahead and do that, and at the same time, I'm going to expand or use the product, distribute the divergence operator to some of the terms, okay? So I'm going to write down an equation where that's been done. So we have that. Now, look at this term. What does that look like to you?
Zero.
Hmm?
Conservation. No.
Not quite.
No.
This should be not. Those are scalars, right? Inside the parentheses. So this will be the gradient with respect to little x. Remember when we defined a material time derivative operator? It was like that. Okay, so if you'll allow me, let's just call this ds dt and put a vs right there. Right, so what that is the material time derivative of that quantity, phi f rho f, moving with the velocity of the solid, right? Because it's riding on the back of the solid. Right? So from now on, because we're going to, like I said, we're going to basically construct this entire problem on the back of the solid, I'm going to drop the s from all the derivations. So, and whenever there's a term, and unless, and I don't think there's a case, but I guess if there's some ambiguity, I might add the s. But from now on, we're basically the velocity, all the terms, because everything is traveling on the back of the solid, we'll just drop the s notation, okay? So with that, then we have d dt also, note that you remember this identity that j dot is equal to j remember that identity? Okay. So another way to write that might be that is equal to j dot over j. Right? So for this term right here, we're going to replace for the second term, we'll replace the divergence of the velocity with j dot over j. Again, with the understanding that j is the determinant of f, where f is the deformation gradient of the solid, right? Solid skeleton. So now we're just going to integrate that equation over the volume, right? Should be comfortable like going from the integral form to the strong form, the pointwise form, by now. So we're just going to integrate this over the volume. This is the current volume. So we have that. And now we're going to use Reynolds transport theorem and on the first term and the divergence theorem on the last term. Okay. So remember, Reynolds transport theorem applies to when you have the derivative of an integral. When you have the derivative of an integral where the volume of the integral could be changing, right? So that's where we, sort of came up with that you need to use the material time derivative in those cases. So we're just going to sort of go the other way, right? We're going to move the derivative to the outside. Second term remains unchanged. And then we're going to use the divergence theorem on the last term to convert the volume integral into a surface integral. Now we're going to pull back to the reference volume of the solid. All right, so remember that is dV equals J dV 0. All right, again, I've dropped the S superscript. Right. So we'll pull back now to the reference volume. Where now our little w has been redefined as capital W, just using the same notation that we before, with small letters for the current configuration and capital letters for the reference configuration. So in this case, big W is defined as this thing, right? It's a Piola transformation. Yeah.
That's J dot, right, in the second.
Yeah. And obviously there's a J that could cancel, but I'm going to leave it right there for now. All right, so now I'm going to define what we'll call the Lagrangian porosity. Well, first of all, let's just talk about phi of f. I mean, if we only have two species and the volume fraction has to add to one, we have a solid and we have a fluid, what's another name then for the fluid? The volume fraction of the fluid? Porosity, right? We've been just calling it the volume fraction of the fluid, but if you think about it, it's just, you know, it's the porosity, right? Whatever's not solid is porosity, right? So the volume fraction of the fluid is the porosity. So while we haven't used that term for phi f, that's what it's always been, right? We could have. The reason I didn't is because, you know, while we kind of have been focusing on this binary mixture of a solid and fluid, essentially everything we derived, including those variations of the conservation of mass constraints and other things, if you remember, those variations were just like phi alpha, right? So they would also hold and work if you had more than one species, or more than two species, like 3 or 4 or 5, right? And so, for example, if you had partial saturation, you could have a third species that would be volume fraction of air, and then your porosity is 1 minus the solid volume fraction, or the fluid plus the air, right? So that's why I never called it the porosity, because, you know, all the ideas hold for more than one species. But in this example, if only two species, the volume fraction of this fluid is the porosity, okay? So remember, the volume fractions are defined in the current configuration, right? So it's the volume of the fluid divided by the total volume in the current configuration, okay? What we're going to call the Lagrangian, I don't know if, I think I mentioned this when I drew those very first potatoes in the reference configuration. You know, I tend to always use the words reference configuration and current configuration.
You also use Eulerian.
Yeah, so that's right. I think I wrote them down as that, but I tend to not say that because then you have to like do that mental association. I think current configuration, reference configuration is very explicit what they mean, right? But there's another word for them. The current is also known as the Eulerian configuration, and the reference is also known as the Lagrangian configuration. So in this case, the literature typically calls this the Lagrangian porosity. Then what it is, so if phi f is the volume of the fluid over the total volume, total current volume, then we'll define what we call the Lagrangian porosity as the volume of the fluid over the total reference volume. And the relationship between the two is that, right? So basically then, anywhere in this equation I see a J phi, I'm going to replace it with a capital phi, right? Yep.
Well, like for the volume fraction current configuration, can that still be assumed like in Eulerian porosity?
Eulerian porosity? Yeah, I mean, technically, if you wanted to call it that, I mean, typically when this Lagrangian porosity, and you'll see as I begin to work through the equations, it's really, for me, it's just a convenience so that, because I'm not going to manipulate, I'm going to basically carry these terms together everywhere. So this just gives me like a simple way. I just redefine this as that, then I don't have to write two symbols instead of one. But really, and the reason I point that out is because really the volume fraction, or most specifically the volume fraction constraint, is always in the current configuration. There's really no notion of like a volume fraction constraint in the reference configuration. Of course, you can pull the equation back, but it's hard to interpret. In the current configuration, you know, which is, when we derive conservation momentum equations, is, you know, in the current configuration, basically we're just saying that the point X is fully saturated. It's all of some species, right? I mean, it's, you know, they add to 1. By the way, there's no, even though I say they add to 1, right, there's nothing that prevents one of them from being 0, right? So it could be that the solid is 1 and the volume and the fluid is 0, right? That's fine. But in the current configuration, they must all add to 1, right? Okay, so basically I'm going to plug this in everywhere you see a J phi, and also I'm dropping, you know, now we're using the term porosity, so I'm going to drop the F. And also, of course, when I'm going to go back to the strong form, so I'm going to use the divergence theorem on this thing. Okay.
So quick question. So even though the volume constraint doesn't act any longer when you pull back, it's still fine because the entire equation was written in respect to current.
Yeah. You can do it. It just doesn't have the physical intuition, because I mean, even this is a little bit weird because it's the current volume of the fluid divided by the total reference volume, right? Yeah. Okay, so with that, after a pullback operation, this equation with that definition and a pullback operation. What the heck happened to my? There it is. That's weird. I guess I started on the 3rd page. Anyway. Okay, so with that, then we have now, this equation is, we pulled back, right? So this equation is in the reference configuration. And just to be clear, whenever I'm going to continue to write d dt, but remember in the reference configuration, d dt is the same as partial t holding x fixed, right? So I'm going to continue with that notation, but just understand in the reference configuration, the material time derivative is just the regular partial derivative. Okay? So recall we had this equation from the conservation of, you know, when we derived the equations from the mixture theory and Hamilton's principle, we ended up with this relation that P, which we called ultimately, we introduced it as a Lagrange multiplier, but ultimately we saw that it just fell out through exercising the variational principle, that it was equal to this, right? And so then, because, you know, if you've taken petrophysics or thermodynamics or anything, then we just sort of recognize that this is the classical definition of pressure, right? So then after that, we started calling it pressure, right? And of course, I knew that was going to be the outcome, and that's why I used the symbol P. Then, you know, from this, we can basically, this implies that there's also an inverse relationship that would identify the density of the fluid as a function of the pressure. Right? And if we call this a barotropic assumption. And really the assumption comes in from the internal energy of the fluid, right? If we assumed in the derivation, right, we didn't write down what these internal energies are, but we just said they're a function of the local density only, right? But if I had, say, comma T for temperature, right, then this would be different, right? Then it would be that the density is a function of pressure and temperature, which we could extend it that way. There's nothing that prevents us from doing it. Just a few more terms, more complicated, right? Okay.
I have a question.
Yep.
So when we change from the strong form to the weak form, why do we not add the constant of integration to the right hand side?
So going from the strong, so this is what you're calling the weak form?
Yes.
All right. It's a misnomer. Let's call it the integral form.
Integral form.
Right. A lot of people call it the weak form, but the weak, you're going to learn in next week where the real weak form comes from, right? The word weak comes from the fact that, when we take a strong form equation, typically what we would do is we would multiply by some function and then integrate. And then we integrate by parts, and what that integration by parts does is it shifts a derivative onto that function that we multiplied by, thereby weakening the continuity requirement. I'll point that out when we see it next week, but that's the real weak form, okay? So let's call it the integral form. Right? So you're wondering, like, why when we go from there to here, there's no constant of integration. And it's just because that equation above must hold. Well, understand that we've also done a divergence theorem, right? So that it's all in terms of volume integrals. It's like one integrand, over the entire volume, right? And that equation must hold for any arbitrary volume that you integrate over. So therefore, the integrand must also equal to 0. Another way to prove that is to think about back to the fundamental lemma of the calculus of variations, right? If you multiply by a test function or a function, right, a variation, and then integrate over the body, you know that the integrand equal to 0 because that test function is arbitrary, meaning it could be the integrand, which would be the integrand squared, and then it would have to be equal to 0. So we're not actually, you understand, we're not integrating that equation. That's why there's no constant. We're just saying that if the equation equals to 0, then the integrand must equal to 0. Good question, though. Okay. So if going back to that, let's look at that first term, okay? So if the first term, now if we're assuming that our fluid density is a function of pressure, let's perform a chain rule operation on it. So d dt phi rho f is equal to d dt phi. Now here's where I'll apply the chain rule. So it'll be that thing. Now recall either from petrophysics or I also used this relationship when I was proving that nonlinear BO coefficient reduced to the linear BO coefficient. I used a definition of bulk modulus, right? So the definition of bulk modulus of the fluid is equal to that. So really, like from petrophysics, we typically this would be the compressibility, but bulk modulus is 1 over the compressibility. So it's this, or you could also write that. So we'll go ahead and substitute this relationship in right there. So let's go ahead and then substitute that back into our conservation of mass equation. So basically, let's see. This is going to go there. What the heck? Going back and looking at this equation again. I could rewrite this like this. And then integrate both sides. Over here on the left, I'm going to integrate from some reference pressure to the current pressure. And over here, I'm going to integrate from the reference density to the current density. And then if I integrate that, the left-hand side just becomes P minus P0 over Kf. The right-hand side becomes the natural log of this guy. And because the fluid is moving with the solid, so if you remember last time, towards the end when we were looking at the conservation of mass and just, I showed that the J of the solid skeleton is the same as J of the solid, right? Because what is J? J is it's a volume change, right? So it's a percentage volume change, right? So if you imagine, like if I have a cube and I reduce it by the volume by 50%, then the volume of the solid also reduces by 50%, right? But also the volume of the pores, or the volume of the fluid, reduces by 50%, right? So if we're not allowing, if the fluid is moving on the back of the solid skeleton, then the overall J is the same as the fluid J, right? So this term right here is 1 over J, right? Because remember, J was like the reference density divided by the current density. So this is also J, 1 over J. Right? So that equals to the natural log of 1 over J. And then using the rules of taking logs, that equals to the natural log of 1 minus the natural log of J. What's the natural log of 1? 0. Okay. So now I have negative natural log of J on this side of the equation, and I have this term on the right. I'll just rewrite it. I'm going to rewrite it, and basically with the, well, let me just rewrite it. Okay, now I'm going to take the time derivative of both sides of the equation. So that gives me on the left 1 over Kf dp dt is equal to so we're going to use the chain rule on this side, right? Chain rule, the derivative of the outside. What's the derivative of the natural log of x? 1 over x, right? Times the derivative of the inside. The time derivative of J is J dot. So then what I end up over here on this side, and I'll move the negative sign to the other side, and then I have J dot equals over J. So if I plug this in, here, then I get and those terms cancel. All right. So now we're going to look at the time derivative of the Lagrangian porosity. And for that, anybody remember from petrophysics we're going to use Athy's pressure porosity relation? So in petrophysics, you probably learned it as something like phi equals the porosity times some reference porosity times E to the minus B sigma prime. B is some fitting parameter. I actually went and looked at that paper recently. It was written in 1930, and they obviously collected a whole bunch of porosity information, pressure porosity information, like applying different confining pressures, and this is the effective stress. So finding different confining pressures with a fixed pore pressure, so that this varied, and then basically that. And he plotted. I looked at the data. It's like thousands of data points, and if you fit a line through it, an exponential fits perfectly. So basically, what we're going to use is just an extension of this, right? So I'm not going to write out all the details, but basically, it's an extension of this that's then been linearized. So I'm just going to write down the final form of the equation. For finite deformations, right? So basically, the linearization works out to something like where B is our BO coefficient from before. Okay. And so then I'm going to go ahead and take the time derivative of that thing, again in the reference configuration, and that is I'm skipping some details here in the interest of time, but I'm just writing the final result here. Now, we're interested in geomaterials. So, what is like a typical value of the bulk modulus of, say, granite? Do you know? And if you don't know the number, I don't even know the actual number, and it varies wildly. I remember, yeah, I remember. I did some work at White Sands Missile Range, and we went up there and we took a lot of cores from, this is when I worked at Sandia, we took a lot of cores from this one like outcropping of weathered granite that we were later gonna shoot some weapons into. And we took a whole bunch of cores, and I remember being shocked at the unconfined compressive strength of some of those cores that were just like 10 feet apart. One of them was like 4,000 KSI, and the other was like 14,000 KSI. So just 10 feet apart. It's like 3 times as strong. By the way, the unconfined compressive strength is often used, but a terrible parameter to characterize the strength of a geomaterial, because almost always geomaterials are confined, right? So what is it, just like in pascals, do you know what the bulk modulus, like what's a bulk, even a Young's modulus of a rock, what is it in pascals? Like what order of magnitude is it? GPA, right, GPA. What order of magnitude is the reservoir pressures typically? Yeah, like MPA, right? MPA. So there's like 3 orders of magnitude difference between those terms, right? And so basically now if you look at these denominators, right? If I assume that P is much, much smaller than K, then this is basically K over K and 1. So and this is almost always a good assumption for geomaterials. It may not be a good assumption for like hydrogels or some other porous material. So then we have the reason I'm keeping the material time derivative instead of choosing the regular partial derivative, just in your mind, if you ever wanted to push this forward to the current configuration, you'd need to then you'd need to use the actual convective terms in that for it to be correct. Right? Okay, so I'm going to write everything together now. Sort of the final equation. Things have been rearranged to put things in terms of this M thing, which I'll define in just a second. So M, and the reason for that is so that in a second when we linearize things, we'll end up with the same equations that people are used to seeing for the linear model. This is called the BO modulus. That term M. And then finally, let's just define, we define W as the Piola transformation of little w. And little w was the difference in the velocities, right? Well, do we have a constitutive model that tells us what the difference in solid and fluid velocities are equal to? Come on, guys. Petroleum engineering. If I have a fluid moving across a solid, or through a solid, then I can define a reference velocity of the fluid with respect to the solid. Yeah, right. Darcy's law. So Darcy's law is just a constitutive model, right? Basically. So let's use it here. So VF minus VS, which we defined as 1 over that's equal to permeability tensor divided by the viscosity times the gradient of P plus times G. This would be the current or Eulerian. And so then if we just apply our Peeler transformation to that, then we get I'll use a gradient with respect to big X now. Where big kappa is equal to J F inverse K F